This video is brought to you by mywayteaching.com.
The next concept of the chapter is heat, internal energy, and work. The zeroth law of thermodynamics led us to the concept of temperature, isn't it? That agrees with the common sense notion. Temperature is a marker of the hotness of a body, or we can say temperature is the measure of hotness of the body. It determines the direction of flow of heat when two bodies are placed in thermal contact. It is the measure of hotness or the degree of hotness of the body, we can say, and it determines the direction of flow of heat when two bodies are in contact. Heat flows from the body at higher temperature to the one at lower temperature. That flow of heat stops only when the temperature in both the bodies become equal. So then we can say the two bodies are in thermal equilibrium, isn't it? So the concept of internal energy of a system is not difficult to understand. It's very simple. We know that every bulk system, you consider any system, every bulk system consists of a large number of molecules, isn't it? So, internal energy is simply the sum of the kinetic energies and potential energies of these molecules. Okay, internal energy is the sum of kinetic energy and potential energy of all these molecules that a bulk system consists of. It's very simple. The kinetic energy of the system as a whole is not relevant. Internal energy is thus the sum of molecular kinetic energy and potential energies in the frame of reference, which is relative to which the center of mass of the system is at rest. Thus, it includes only the energy which is associated with the random motion of molecules of the system. So, we denote the internal energy of the system using the letter U. Okay. Though we have invoked the molecular picture to understand the meaning of internal energy, as far as thermodynamics is concerned, this internal energy is a macroscopic variable of the system. The important thing about internal energy is that it depends only on the state of the system, not on how that state was achieved. So, internal energy, which is represented by the letter U, it depends only on the state of the system. It does not depend on how that state is achieved. It just depends on that final state of the system. And internal energy of a system is an example of a thermodynamic state variable. its value depends only on the given state of the system, not on the history. That is, not on the path which is taken to arrive at that state. Thus, internal energy of a given mass of gas, it depends on its state described by the specific values of pressure, volume, and temperature. It does not depend on how that state of gas came about. Okay. Pressure, volume, temperature, and internal energy are thermodynamic state variables of the system. Internal energy is also a state variable. Along with internal energy, we have various thermodynamic state variables. They are pressure, volume, temperature, and internal energy. So these are the thermodynamic state variables, isn't it? If we neglect the small intermolecular forces in a gas, the internal energy of a gas is just the sum of kinetic energies associated with various random motions of its molecules. Okay, gas is not only translational, another in the volume. Okay, it is also, which means gas also includes the rotational as well as vibrational motion of the molecules. Okay, you can see that in the figure. You can see in the figure the internal energy u of a gas is the sum of kinetic and potential energies of its molecules when the box is at rest. Kinetic energy due to various types of motion, that is translational, rotational, as well as vibrational. Okay, if the same box is moving as a whole with some velocity, the kinetic energy of the box is not to be included in the internal energy. Okay, this is the figure. What are the different ways of changing the energy of a system or changing the internal energy of the system? Just think. How can we change the internal energy of the system? You just consider again, for simplicity, system to be a certain mass of gas which is contained in a cylinder with a movable piston, as you can see in the figure. So here you can see here the figure in which it consists of a the gas having certain mass in a cylinder with a movable piston. Experience shows there are two ways of changing the state of the gas. One way is to put the cylinder in contact with the body at higher temperature than that of the gas in the cylinder. So the temperature difference will cause the flow of energy or heat from the hotter body to the gas, isn't it? Thus increasing the internal energy of the gas. The other way is to push the piston down, that is to do work on the system, which again results in increasing the internal energy of the gas. Of course, both these things could happen in the reverse direction with surroundings at a lower temperature. Heat would, if the surrounding is at lower temperature than the gas in this particular cylinder, in that particular case, heat would flow from the gas to the surroundings. Likewise, the gas could push the piston up and do work on the surroundings in order to make the attain the equilibrium state. In short, heat and work are two different modes of altering the state of a thermodynamic system and changing its internal energy. Okay, so heat and work done. See, the notion of heat, it should be carefully distinguished from the notion of internal energy. Heat is certainly energy, but it is the energy in transit. This is not, it means the distinction is of basic significance. I say you what it is. The state of a thermodynamic system is characterized by its internal energy, not by its heat. A statement a gas in a given state has a certain amount of heat. Just see this statement. A gas in a given state has a certain amount of heat is as meaningless as the statement that a gas in a given state has a certain amount of work. In contrast, we can say a gas in a given state has certain amount of internal energy is a perfectly meaningful statement. Similarly, the statements that is a certain amount of heat is supplied to the system or a certain amount of work was done by the system are correct. So we can, as a whole, we can say heat and work in thermodynamics are not state variables, they are modes of energy transfer to a system. Okay, heat and work, they are not state variables in thermodynamics. They are, we can say, modes of energy transfer to a system, resulting in change in its internal energy. We'll usually get confusion between this heat and internal energy. The distinction between them is sometimes ignored in very elementary cases, but that distinction is very much important. Okay, we can't neglect that. So here we understood the importance of heat, internal energy, and work. So we also understood that internal energy is a thermodynamic state variable, isn't it? Along with that volume, pressure, temperature, energy is important, one of the thermodynamic state variable. Whereas heat and work, they're not thermodynamic state variables. They're just the modes of energy transfer, but they once heat and work, they change the internal energy of the system. That we should keep in our mind. Even though they are not thermodynamic state variables, they change the internal energy of the system.